So let's talk about something very interesting actually. This is a very useful technique. Okay, I mean, being able to find integrals can actually help you to solve many problems. Okay, in economics. Okay, you can actually use even areas to solve the optimization problems. Okay, I mean, there is a connection. Okay, and then of course there are some concepts which are directly related to finding integrals. Let's say if you are interested in finding probabilities, or you're interested in finding the mass of individuals located in a particular interval, or if you want to find average income of people in a particular interval, people earning between some lower limit and the upper limit, if you want to find that average. So integrals can be very useful. Today, just make sure you pay attention to this particular aspect, especially how is integral connected to areas, because once you get that, then you will have no trouble understanding what we are going to do in the next class. Okay, so this is a very important part of the lecture. Okay, so let me talk about this area first. Okay, so how is this area connected to integrals? Okay, and that's really fun. Okay, uh, well, we know how to find areas of rectangles, squares, but we can actually find areas below any continuous function. Okay, I mean, between basically the x-axis and any continuous function. In fact, we can also find areas between the two functions. Okay, I mean, it's kind of very useful trick, and the derivatives can help you to do that. Integrals can help you to do that. Okay, so let's see how. Okay, so what I'm going to do is I'll plot a function and I'll present the problem, and then we'll see how we can use integrals to do it. Is that okay? Fine. Okay, so suppose we have this function small f of x, and we have x on the horizontal axis. Okay, for the time being, let's assume that f is increasing, but that's not really required. Okay, I mean, it will be easier to explain me why it is area with this particular assumption, but that is not a required assumption. So even if f is not an increasing function, whatever I'm going to say will work. Is that fine? If it's a decreasing, or as long as f is continuous, it will work. Okay, so the only assumption that I'm making here is this: f is non-negative and f is continuous. Okay, so f is non-negative. So when I say f is non-negative, that means it takes non-negative values. Okay, basically it is on the above the horizontal axis. Its graph is above the horizontal axis. Okay, and f is continuous. Okay, and just to explain you this, I'm going to put this additional assumption, which is f is also increasing. Okay, just to for explanation's sake. Okay, okay, now suppose I want to solve this problem. I want to find this area. Okay, basically I want to find this area. Okay, basically what is this area? That's the question mark. Okay, fine, that's the question that I want to answer now. Is that okay? Fine. Okay, so we have a continuous function, non-negative, f. Okay, and I want to find the area below this function above the horizontal axis. Okay, between a and b. Okay, where a is this, b is this. Okay, okay, so let's see how to do this. Okay, I'll define a function at. Okay, let me define a function at. Okay, so what is at? At is basically this area. Where this is t. Okay, so at is basically this area. Is that okay? So basically at is area below the function between a and t. That's how you can think about it. Okay, is that clear? Okay, now can you tell me what is a in terms of at? So what should I put in place of T so that I get A? So that I get this area. Exactly. AB is the area that I want. Do you agree? So if I can find this function AT, do you agree finding AB is just plugging in B there? I'll get the area. So I'll not only find AB, I'll actually tell you how to find this entire function AT. Is that fine? Clear to everyone? Understood? Okay. So let's try and find this function AT. Okay. Fine. Okay. Great. Well, T can be anything. Okay. T can be any number between A and B. Okay. So basically, I'll tell you this function AT. Okay. Now, before I tell you this function AT, let me ask you something. Is AT increasing in T? Huh? Yes, it is. As T increases, you can see that area is increasing. Can you tell me what is AA? Very good. Okay, so all these things, something that we know. AD is increasing, AA is 0. Okay, so all these things we know so far. Okay, so I know the area at A. I don't know what is the area at T. Okay, and I know that area is increasing. Okay, fine, for this particular function. Okay, why is A 0? So suppose you just take this T, shrink it to A, and what is the area? Yeah, right. A is 0. Okay, and I want to find AB, right? I want to find AB eventually. Okay, that is what I want to find. Okay, so I'll not only find AB, but I'll find this entire function AT. Okay, so AB will be just a special case of this. Okay, so let's do that. Okay, so how do we do this? Now, what I can do is, let me consider another point T plus H. Okay, so H is, let's say, some positive number. Okay, some small. So remember, H, we used to take H tends to 0, something like that. Okay, H is some positive number. Okay, so this is T plus H. Is that okay? Fine. Now, what I'm going to do is, can you tell me geometrically what does this mean? Absolutely. Okay, it is basically this area. Okay, so let me just shade that. All of you agree that it is this area? Yes or no? Okay, good. Now what I'm going to do is this. I'll ask you some question. Okay, and you'll have to tell me whether that is true or false. Okay, suppose I do something like this. Sorry. Suppose I take f of t. Now what is f of t? F of t is the value of the function at t, right? Okay, and I multiply it by h. What will I get? F of t times h. It's a rectangle, area of the rectangle. Now which rectangle is it? So okay, can you tell me, is there any relation between these two terms, this and this? They are the same. Are you sure? This is a rectangle, this doesn't look like a rectangle. F of t into h is the area of the rectangle whose base is h, height is f of t. But this area is not the area of the rectangle, right? I mean something, because the curve might not. Okay, let's not talk about right now what happens as s tends to 0. Right now, just give me this answer using these assumptions, using the fact that f is increasing. Is there any connection? Yeah. So can we say that left hand side is greater than the right hand side, or less than the right hand side? Less than, because the f is increasing. So obviously, if you're going to draw a rectangle, it will be below this, right? I mean below this strip. Yes or no? It will be a subset of this strip. Do you agree? So obviously its area will be smaller than or equal to this area. Do you agree? Because f is increasing. Yes or no? Understood? Okay. Now let me ask you another question. What about this one? What can you say about this? This is also a rectangle, right? This is also a rectangle and f is increasing. So what can you say about this area? Absolutely, it will be greater because it's just going to be a bigger rectangle. Yes or no? Yes, because f is increasing. So, I've just taken the highest value of f in that interval and multiplied by the base. So obviously, if I take the highest value multiplied by the base, it will give me a bigger area compared to, the area below the graph. Okay, and similarly, this will give me the smaller area. So do you agree the term in the middle is a squeeze between these two? Yes. Now h is positive. If I divide this entire thing by h, do you agree the inequality will be true still? Okay, can I do this division? Okay, let's do that. So I'm just dividing it by h. Okay, sorry. Do you agree I'm going to get this? All of you? Yes. Now this is true for all h, right? This is true. This inequality is true for all h. Yes or no? For all h positive, this is true. Yes or no? Now if this is true for all h, if I take limit as h goes to 0, this will still be true by squeeze theorem. Yes or no? Okay, so let's take the limit. Can you tell me what is the limit as h goes to 0 of the left hand side? F of t, because there is no term h there, so obviously it's just a constant. If you're going to take its limit, the constant will stay constant. Okay, so you're going to get f of t on the left hand side. Very good. What about the right hand side? Is it f of t? Why? So which assumption is used? What do you think? Why do you think I can plug 0 there? I mean, right? I mean, I don't really care about what happens at 0 when I'm finding the limit. Because it is continuous. Absolutely, because it is continuous at t. That is why I can use this substitution property, because that continuity gives us this. Yes or no? Is that clear? So let's do that. Yes, that's the definition of continuity. Remember, limit as h goes to 0 or limit as x goes to, so we say that a particular function is continuous at a if limit as x goes to a, f of x is f of a. So basically if you plug x equal to a, you'll get the limit. That's the definition of continuity. Okay, so you can do this because of our assumption that f is continuous. Okay, so right hand side goes to f of t, left hand side goes to f of t. Can you tell me what does this middle term go to by squeeze theorem? F of t, because it is going to f of t. Now can you tell me what is the interpretation of the middle term? Derivative. Absolutely. So basically you have done something really interesting. You have found the derivative of this area function at t, and you have found that this is nothing but f of t. Okay, so the middle term, the limit of the middle term is actually the derivative of the area function at t, and that is exactly equal to f of t. Yes, great. Now, so what do I want to find? Area. Now if area function, if the derivative of the area function is f, small f, then area function must be one of the indefinite integrals. By definition, it must be one of the indefinite integrals. I mean, we have to still find which one it is. Okay, but it is definitely one of the indefinite integrals of small f. Do you agree? Okay, so this tells us that at is one of the indefinite integrals. of function f. So I mean, always remember, we have this function f which is given to us. Now we know one very useful fact, and that fact is, take its indefinite integral. One of those indefinite integrals must be the area function, which is a good thing, but we haven't done the problem completely yet, because what constant should I add so that I get, so we are not done yet. Is that clear to everyone? We are not done yet. Okay. But we have solved the problem, more or less. Okay. But let's now solve it completely. Okay. So let's now find which of the indefinite integrals will give me the area function, because once I have the area function, then I can find the areas. Okay. And that's really nice. Okay. So what you can do is take any indefinite integral of f. I mean, of course, you know how to find an indefinite integral of small f, right? Now you have to figure out which one is it, but that's fine. You can take any one of them. Can you do that? Okay. Can you just say that let f be some arbitrary Now you don't know which one is it, so you can take any one of them. Okay, just take any one of them, and I'll tell you using that how you can find this one. Is that okay? Fine. So let's do that. So let f be some indefinite integral of f. Okay, let f be some indefinite integral of f. Like for example, can you think of any indefinite integral of x cubed? X to the power 4 by 4, maybe you can just add 1 to it. That's one of the indefinite integrals. So you can think of many. Just take any one of them. Whichever you like, you can take any one of them. Right? We can always do that. Okay. Now, can you tell me what is the connection between f of t and a of t? Are they equal? Are they always equal? So no, like you took some indefinite integral, somebody else took some other indefinite integral, and you're saying both of them are going to get the same area. Okay. Do you agree that the difference between these two will be some constant c? I mean, that's the only difference, right? I mean, if you took ft, and I want to find at, the difference between us will be just some constant c, no matter what t we pick. Do you agree? Because basically they're just shifting by constants, right? I mean, that's the only difference. If you took something else, I took something else, then our difference will be just c, right? I mean, everywhere. So do you agree that this is c? This equality will hold, no matter what indefinite integral you're going to pick. Do you agree? Yes. Okay, let me come to that. I still haven't solved the problem. Okay, now just think about the steps that we are doing. We have identified area function as one of the indefinite integrals, but we still haven't identified which one is it. For that, I'm just taking any indefinite integral of your choice. Okay, take that, and I'm going to use that to find the area function. Is that okay? Fine. Is this clear? Okay, now you have chosen capital F. You have chosen capital F. So you know everything about F. You know the entire function F. Do you agree? You still don't know what is the entire function A, which is what I want to find, but you know F, right? Yes or no? Yes. Okay. Now, what is F of A? A of A plus C. And what is A of A? 0. So what is F of A? F of A is C. So this tells you what? What is A of T? So you know F. So you know F of T, and you know F of A also. So now you know A of T. Interesting, right? Okay, that's it. That's the area function. Okay, now let's do one application. Okay, let's do that quickly. Okay, now it's just straightforward. Okay, But please note that even though in the proof I use the fact that f is increasing, but that's not required. For f decreasing also you can do the same thing. Okay. Okay. So it's completely fine. The argument that we gave is actually general. It's also true for any other function which is not necessarily increasing or decreasing. Okay. As long as it is continuous, it is going to work. Is that fine? Okay. Fine. So now that we have this, let's use that to find an area of, let's say this function. Okay, so let's see. Suppose f of t is, suppose f of x is x squared. Okay, so simple problem. Suppose f of x is x squared, and I want to find this area. Can you tell me how do you find this area? F is non-negative, no problem. It's continuous. So can you tell me how do you find this area? Area below this graph. So first take any indefinite integral of your choice. Can you think of any indefinite integral? Huh? What is the indefinite integral of x squared? X cubed by 3. So you're saying x cubed by 3 plus 1. That's what you want to take. Okay, let's take that. Do you agree that's one of the indefinite integrals? Yes or no? Okay. Now just use this formula. Okay, I want to find a1. A1 is what? F of 1 minus, what is this a here? 0. Okay, tell me what are we going to get? Notice that this constant doesn't matter. It's just going to, so that is why I said that you can take any indefinite integral. It's not going to be a problem. Okay. So it doesn't matter. It's just going to cancel. So obviously, the convention is that you just ignore this constant. Just take that indefinite integral. But the idea here is that no matter what indefinite integral you take, it doesn't matter. Okay. If you're going to do this, you'll get the answer. Okay. So that's basically the area. Okay. So we have found the area, which is a very interesting thing, right? I mean, uh, just by using calculus, we are able to actually find the area below some function which is not really a straight line or something like that. I mean, it's a very different geometrical object. Okay, and it's very good. Okay, to know how to find areas. Okay, is that clear? Okay, now that we are done with this, let me give you the definition of definite integral. Okay, so still I haven't told you what definite integral is. So definite integral is actually a concept which is closely related to the area function. Okay, so if you just look at this difference, okay, the definition of definite integral comes from this difference. Okay, so let me now give you the definition of definite integral. So definite integral, suppose you want to find integral, the definite integral a to b fx dx. Okay, suppose you want to find definite integral of a to b fx dx. So basically it turns out that it is equivalent to finding the area below the graph small f of the function small f between a and b. Okay, it is equivalent to that. But what if f is negative? So basically we are going to use the same definition, but it is not always going to give you the area. Okay, because if f is negative, then you'll get something else. Are you getting my point? Okay, sometimes you get a negative value, sometimes you get something else, but the motivation for the definition actually flows from this area function. Okay, so integral a to b fx dx is nothing but this difference, where capital F is one of the indefinite integrals. Any one, you pick any one of them, and then just find f of b minus f of a. That's basically uh, the definite integral. Okay, is that clear? That's the definition. Is this clear to everyone? Okay, and when f is non-negative and continuous, this will give you the area between a and b below the graph of f. Is that okay? This will give you exactly the area, you know, when f is non-negative and continuous. Is that fine? Okay, so let's discuss some properties of definite integrals. Okay, okay. By the way, this is another way in which you write the definite integral. You know, I mean, just in case if you see something like this, okay, it's just the same thing. Okay, I mean, just take the indefinite integral, one of the indefinite integrals, and just write it like this. Okay, and that's basically just this term. You know, I mean, just in case if you come across this somewhere in the books, I mean, this is what it means. Okay,